So, you'll be pleased to know finally we've stopped doing reduction semantics. The first part of the course was grammars, the second part was reduction semantics, and the third part is static semantics. And it's static, so no evaluation is required. So we're leaving evaluation behind, no more of that. We're just going to look at the program. If we're running it, that's the dynamic behavior. We're not running the program, we're just looking at the program and thinking about, is it a good program? We've done syntax checking, we've done reductions, now we're just going to look at the program and see, is it any good? So we want to look at our program, we know it's valid syntax, and we're going to find, are there any errors there? And in particular, there's a particular type of error we're looking for. So we're looking for these errors. If you remember in the last lecture, and sometimes I've said, things can go wrong. Programs can run forever. Sometimes they'll run forever if you use call by name. Sometimes they'll run forever if you use call by value. Sometimes they'll give you an answer if you've got the right memory, values for all the variables. But if you don't have values for all the variables, you won't get an answer. That's another type of error. But here, we're going to look for errors like this. So the key point about these errors is that we can look at it, and you and I can tell this is an error. Because 6 is a number, and now x plus 2. If you think about this, because it's got plus and 2, that means x must be a number. So this is something that takes x as input, sorry, a number as input, and returns a number. So this is a function taking a number as input and returning a number. Now here's the key point. I can do that in my head. If I can do it in my head, all I need to do is think about my process for working that out, and then I can turn my thinking into a program. And once I've got a program, the computer can do what I just did. And the computer can say, no need to run it, I can tell this doesn't work. So here's our goal. So that's what we're going to do. We're going to turn the reasoning that we could all just do. A few of you have already asked us, what happens if we try to evaluate that? You guys, you've already spotted it's an error. So you're going to turn that into an algorithm so that the computer can do it for us. And it's a specific type of error. These are called fresh color. Look, I found a pen. I don't need to hunt for pens. What should we have? Black and red. So we're going to look for type errors. It's a type error because the type of the first thing was a natural number, 6. No, sorry. The type of the second thing was a natural number, 6. And the type of the third thing, or the first thing, was a function from natural numbers to natural numbers. So it's all about types. We're just going to look at the types of everything and check they match up. Check that if we've got plus, both things that are being added have the type natural numbers. We're going to check if it's a function that the input of the function, sorry, check if it's an application, the input of the function, it has type the same as the argument. In other words, if I have a function and I'm expecting a natural number, then the input better be a natural number. So, in detail, so we're going to look for any time we see t plus s and check both of them are numbers. And also look for terms f applied to s. What? Slightly down? Okay. We're going to look for, thank you very much, we're going to look for f applied to s. Drink some Coke. And check that f is a function whose input type is the same as the type of s. Stuff like that. Okay. Now. Okay. So, what are these types? That's the first question to say. So guess what? Here comes another grammar. It's very, very simple.
Can we get that back, please?
Okay. Gosh, this is brilliant. So the idea is that every expression is going to get given a type, and then that will allow us to check these things. Done? Take it off? So the idea, give every term a type. So 6 will have the type natural numbers, 12 will have the type natural numbers, etc., etc. And then functions will have types that represent what they take as input and what they take as output. So I can now tell you what these types are. So type well, it's either, so using n on that. So that's a symbol. You can use any symbol you want, but it stands for natural numbers. If I wanted, I could have written NAT, I could have written natural numbers. It's just a symbol. So if you see that symbol, that's a type, and we think of it as a type of natural numbers. And also, there's a type for functions. So these are function types. So we just write an arrow, one type on the left-hand side and one type on the right-hand side. So something has this type. If it is a natural number. And then something has this type. Or a term, in fact, not something, a term. It's this type, has this type. If it is a function, if it's a function that takes a term of the first type as input, term of the first type as input, and returns something of the second type, output.
What's the first word in that paragraph?
A term. A term has a type like that. It is a function that takes a term of the first type as input and returns something of the second type as output. So types, so here are some example types. Well, you know that that's a type because that's the first line. Here's another type. So things have this type of their functions that take a number as input and return a number. But you could also have, this is a type. So this would take a number as input and then return a function as output. And that function, the output, is itself a function that takes a number as input and returns a number as output. And similarly, you could have n. So this is a function that takes as input a function that takes a number as input and returns a number as output. And then it will return a number as output. So you can just make them more and more complex. So those are some example types. And all we're going to try and do in this lecture is figure out when do terms, exactly this. We're going to try and give every term a type. Now, not every term will have a type. Sometimes it won't work. The one I did on the first slide, lambda x arrow x plus 2 applied to 6, no, plus 6, that doesn't have a type. And we've spotted an error. So we're going to try and make sure that, figure out which terms do have a type. Okay, Stuart? Right. Let's do an example or two. Oh, let's do something interesting. Let's think. So, here's an example to get us going. We're going to try and work out whether this term has a type or not. We'll do it properly in detail with the formal system in due course, but here's an example. So first of all, who reckons this has a type? If you do, hands up. Anyone brave, willing to? Oh, you think it does? Good. I mean, good that you're thinking. I'm not saying you're right or wrong. Who thinks it doesn't? You think not? Okay, fair enough. You're scratching your nose, or you don't think it?
No, just scratch my nose.
Scratching your nose, that's fine. That's not a type, by the way, but that's a valid action. Okay, let's think about it. So again, I'm not giving you the program, I'm not giving you the algorithm. I'm just trying to get you used to the sort of thinking you might do intuitively. Once you're very, very good at this, you'll be able to do this. Well, if you look at it, it's not a number. I know that, because it's lambda x arrow x4 plus 6. So the main thing is it's a lambda abstraction. So it can't be a number. It is a function. If it's going to be anything, this is a function. So if this has a type, it is a function. So something like that. Okay. So now let's look at the output. So we have to fill in the input type, or try and fill in the input type, or try and fill in the output type. So let's look at the output type. The output is whatever this returns. Something plus something. What do you reckon? What type would that have if it has a type? Yeah, it's a plus, so it's a number, natural number. Integers have negatives, we're only using positives. So yes, so if it has a type, because it's a plus, it's returning a plus thing, the output must be a number. Okay? So we're going through this, we're trying, it's like a detective story. We're looking at the clues, we're trying to find information about what the type will be. So now let's look at the input type. So the input is whatever the type of x is. X is the input. And we know, what do we know? The only other thing we know about x is it gets applied to 4. So the input must be a function, because it's being applied to 4. So if this is going to have a type, it must look like this. So this is the type of x. Now, it's a function, it's being applied to 4. So 4 is the input. So the input must be a number. And then the output, x applied to 4, the output, the result, is added on to 6. So therefore the output must be a number. So, yep, that has a type, and that's its type. So informally, it's just looking for information about when things are used, how are they used, are they numbers, are they functions. Those are the only two types. So when you're looking at something, you ask yourself, is it a function, is it a number? And that'll tell you some information, and then you look at the component. If it's a number, you're done. If it's a function, look at the output. What is it producing? Is it a number, is it a function? Look at the input. Is it a number, is it a function? Okay, great. So that's an example. So 1. Here's another example. X plus 3. Oh, in brackets, of course. Right. Does that have a type? Anyone want to offer me an answer? You can see you're thinking hard. It's always a good sign. Do you think that has a type?
Can't tell.
That's true. I can't tell either. So that's the right answer. Why can't we tell? What do you think? Could that be a number? It could be a number. This will be a number. When will it be a number?
When x is a number.
When x is a number. So if x is a number, yes, it'll have a type. But if x is not a number, if x is a function, no, it won't have a type. So it depends on the free variables. This is just like when you're evaluating expressions. If you've got an x, if you've got a free variable, you need to know what it is. You can't do anything if you don't know what it is. So in order to give types to expressions, we must give types to the free variables. So the key point to give a type to an expression, we need first to give types to the free variables. So, just like with evaluation, of course we need something a bit like a memory which gives us information about the free variables. Here we're interested in types, so we need information about the types of the free variables. Can I remove this? No objections? Going once, going twice. So that means our judge, we're going to have another judgment form, you'll be pleased to know. So we call the store, or the environment, we call it a context here. The environment is called a context. So what is a context? Well, just like stores, they could be empty, or It could be a context you've already built up, and then you need to have a variable, and then we write colon for has type, and then we give it a type. And then a typing judgment looks like this. So it's context, so these are like the environments we had before. As you can see, they're either empty or there's something already built up and something about a variable, and now we've just changed it. All we're saying is the variable has a type. So either we write n for natural numbers or we have a function type. And then if we have a context, then we can say when a term has a type. And we use this symbol here, colon, for has type, and this, maybe I should write it longer, it's a vertical bar and then a slight horizontal bar. Again, this goes back to the 30s, 1930s, when people started using these symbols. Okay, so just like we were doing evaluation, we're following the same pattern. We want to do something, we need the notion of environment, then we have a judgment form, and then all we have to do is give rules for each of the pieces of syntax in the Lambda counters, and then we're done. So all I now need to do is give the rules for each term constructor. Just like you had, how do you reduce a new, how do I reduce a plus, how do I reduce a do, how do I reduce an if, or how do I reduce a lambda, how do I use an application, etc., etc. Same, I just need to say, how do I type, typing rules. And because you're super clever, I know that all of you actually know the answers already. So I'm just going to ask you to give me them. Yes! Okay, let's do a simple one. What's the simplest one? Probably plus. So, here's a context, and the Greek letter we tend to use is gamma. That's a capital gamma. So, when does T plus S have a type? And I'm not going to worry about trying to give T plus S a function type. I know it doesn't have function types. So there's no rule for giving a function type. But there is a rule for saying when T plus S is a natural number. So because you're all very clever, I can ask all of you to help me out. So I think it's your turn next. How do I check that T, what would I need to check in order to show that T plus S is a number? Yeah? Yes?
When T is a natural number?
Yeah, that's great. If T plus S is going to be a number, then T better be a number. So, what should I write? So that's what I need to do in my head. How do I write that down? What symbol should I write here? You can give me any bit of it.
T.
T. All right, well, certainly we want to check T as a natural number, so we better write down T. You give me another bit?
Arrow N.
No arrows, so arrows are types and function types. We're not dealing with function types. Have another, you have a go.
Saying that's part of the natural numbers.
Yeah, so what's the symbol I'm going to write for the natural numbers?
So backwards E. It's like an L and all.
Right, so you write colon. So I know you've done some discrete mathematics, and you've done some set theory, and you write this symbol. So this means T is an element of the set S. Okay? And this is very similar, but not quite the same. This means T has type S. So it looks very similar. And for some people, they think of types as sets, and in fact, we'll be doing that later on. But just for the moment, this thing is not a set of natural numbers, it's the type of natural numbers. And there's huge amounts of philosophy about what the difference is between a set and a type, and we'll talk about it later. But just for the moment, it's got to be a type. So the type of natural numbers is that. Okay? So you're just about spot on, but not quite precise. So you've got the easy point now. What should I write here? Yes, because we want to say T is not a member of the set of natural numbers. We want to say T has type. Nat. Very good, except this is not quite a judgment, a typing judgment. If you look at the typing judgments, they have to look like this. T might contain free variables. If I just write down this, I don't know what the free variables of T might be. So I need to do a bit more work. What should I write down? So remember the point about the context. So you see, we've got a term, we've got a colon, we've got a type, but we're missing this bit and we're missing that bit.